So now let's start looking at trig functions. So we're going to do the same process to find the inverse for sine. So we go ahead and we swap our x's and our y's. Remember, we talked about this when we were solving triangles. The only way to isolate that input, because y now is an input, it was an output, but the whole purpose of finding an inverse is to swap your inputs and outputs, is you have to go ahead and compose both sides with the inverse. So you take the inverse sign on that side and on this side. So what you get there is, and this was a Math 111 topic, is when you compose inverse sine with just sine, you're left with just the input. And there you are with the inverse sine function. So when you're looking at the graph for sine of x, all right, well, here's this beautiful graph that hopefully we have locked in our memory. Would you consider this function to be 1-to-1? So one way we can check is through that horizontal line test. And no, it is not. But just like we did with y equals x squared, maybe we can just focus on a portion of this graph where it is 1-to-1. And because we don't want to have all these different parts we're looking at the graph, mathematicians have agreed on a certain interval. Now we want to choose an interval where we'll hit every key point. Now remember, because sine is periodic, it repeats itself. But we have to hit every single point. So that is why they decided to look from negative pi over 2 to pi over 2. Because then they're hitting those low points, they're hitting the midline, they're hitting the high points and all the points in between. We wouldn't want to look at, like just from here to here, because then we're not going to get all of the outputs or all of the inputs, but we know we can't get all the inputs. So that's why they decided it's going to be from negative pi over 2 to pi over 2. Now, only on that little section of that graph is our inverse going to be a function, okay? So what I've done down here is I just took that section of the graph, right? From negative pi over 2 to pi over 2. We are going to graph the inverse sine function on top of this graph. Now here, this is the really nice thing in this class. You don't have to graph these inverse functions, all right? I am just doing my best to explain how these functions exist and what they do and how they look, because I think that's important. So don't get so caught up. We don't have to graph them, but I do want you to see it visually of what is happening. So remember, to graph your inverse function, well, the inverse is we swap our x's and our y's. So 0, 0, well, let me change colors. That will be good. If I swap 0, 0, it's just 0, 0. And then if I swap pi over 2, 1, well, that's going to become 1 pi over 2. So let me go ahead and go back to Desmos, and I'm just going to find what pi over 2 is equivalent to, so I can approximate about 1.57. All right, so let me go back to my notes. So I need to swap about 1.571. So to be clear, I'm here, I'm swapping this point. Okay, so now my input becomes 1, okay, which is going to be roughly around here somewhere. And my output becomes 1.57. So to swap that pi over 2, 1, that's going to become 1 pi over 2. So that is going to be about right here. And I'm going to go up a little bit. It looks like it's going to go right in the middle of, trying to approximate it without having the correct axes. So, all right, so it's going to go right here. and then up. So I believe it's about 1 pi over 2. Remember, pi over 2 is about 1.57. So I'm going right. It's like, oh geez, let's see, make sure I do it right. It's going to be about right here. So that coordinate is 1 pi over 2. It's hard to do because we're talking about irrational numbers, so I'm approximating there. And then I got to swap this coordinate, right? So now that coordinate is going to become -1, negative pi over 2. So that's going to go about right here. And we're going to go all the way to like right here. And so what we end up getting is this inverse function for sine. So this is our inverse function for sine. All right, well, with sine of x, when we're looking at our domain, that's that red graph. Remember, we just were looking at negative pi over 2 to pi over 2. If I was looking at the whole graph, it would be from negative infinity to infinity, okay? But I'm just looking at this section. Now my range for that red graph would be -1 to 1. All right, well, remember the whole idea is you swap your domain and ranges. So my inverse graph, though, I have a visual here, which is nice. My domain would be -1 to 1. And my range would be negative pi over 2 to pi over 2. Now remind yourself that, remember, these inverse functions, the whole reason they exist for us is it produces an angle. So it makes sense that my range, my output, would be angles. All right. Now, knowing this domain and range is really, really, really important when we get into actually evaluating certain things. All right, so what I've done in this next part is that I just listed every single angle within, I'm going to go up here for a moment, within this piece that we only looked at, right? So we're only looking at this piece of our sine graph. And we're going to just list what these angles put out for just the sine function, because this little chart is going to really help us evaluate. So I'm going to pull up that unit circle. And let's go ahead and just bring it to, let's cut that and let's go back. And let's pull it here. And I'm just going to make it a little bit smaller so I can just actually use it. All right. So looking at this, negative pi over 2 is right here. So my sine value is -1. So you could look at the graph too. Negative pi over 3 is here. My sine value is -√3 over 2. Negative pi over 4 is -√2 over 2. Keep going. Negative pi over 6 is here. My sine value is -1/2. 0 produces 0. Pi over 6 is 1/2. Pi over 4 is √2 over 2. Pi over 3 is √3 over 2. And pi over 2 is 1. Now remember, I'm going to get rid of that for now. We talked about how sine's an odd function, and you can see that right now. When you put in negatives, it affects your output. Versus when we put in positives, I got a different output. So you can kind of see right there just in the chart alone that that's an odd function. Now, why this is helpful is now I can really use that chart to help me evaluate certain values for the inverse sine. Now here's something, is I've been saying inverse sine. I want you to realize arc sine means the same thing. We talked about that briefly when we first met. So I'm going to be using arc and then this notation. I'm just going to go back and forth with those things so you can recognize both. So if I ask for the inverse sine of 0, now there's only one angle that will produce 0 within this defined domain we have to look at on our sine graph, right? We were only looking at from negative pi over 2 to pi over 2. So there's only one answer. We don't want to list multiples because our inverse sine, right, then wouldn't be a function, okay? It has to remain a function. So what angle produces 0 for sine? That's how you can read that. So either I say the inverse sine of 0. The other way to say that is what angle would produce 0 for sine? All right, well, I look here. Here's 0. Looks like my angle 0. Arc sine of 1. Well, remember, whenever you're looking for the inverse, your answer is going to be an angle. Here's 1. So my answer is pi over 2. So let me rewrite this. This is just another way to say sine of pi over 2 equals 1. That we've been doing. Now we're just working kind of like backwards. We're swapping them. What angle for sine produces negative root 2 over 2? Okay, that's here. So my angle is negative pi over 4. All right, and then how about D? Inverse sine of negative root 3 over 2. That is going to be angle negative pi over 3. So when they say find the exact values, they, me, whoever, you want it in radians. So I don't want decimals at all, unless it says use a calculator. All right. But for the majority of this work, we're going to be using, knowing that unit circle. Now, of course, it can't be that easy, right? We would run out of problems really fast because we don't have many things there on our chart. So let's make it a little more interesting. So let's one more time talk about something you've learned before in these 111 days. And so I even said I wasn't lying about those skills. So we found that inverse. Ours looked a little bit different than this one. That's just because here I got us a common denominator. All right. Now, we talked about this actually even in this video alone, but when you have the inverse, right, and you want to prove that they are inverses of each other. Again, this was from a previous class, so I'm going to go through this kind of quickly. What we did is, if they are in fact inverses of each other, when you compose them, it should always spit out your input. Now you have to show both ways. So you have to compose it this way as well. Now, if it doesn't equal X, then they're not inverses or you did something wrong in your arithmetic. However, we know these are in fact inverses, so it should work out. So a little bit of a blast from the past. So I'm going to go ahead and refresh your memory on how you do compositions. I'm going to replace this with what it equals. 1 minus 3x over x. And now what that is saying is, I'm going to look in my function f. Everywhere I see an x, I'm going to replace it with that stuff in the parentheses, because that's my new input. So you end up getting 1 over, you put this in there, and then you add 3. All right, well, I can't leave it like that. And that certainly doesn't look like it equals X to me. So I definitely have to clean this up. So one way you can do it, there's a couple ways, but I'm going to teach it this way. I'm going to multiply top and bottom by X because I'm just multiplying by 1, so I'm not changing the problem at all. I distribute the X to all my terms in the numerator and in the denominator. So what you end up getting is you get x in that numerator. When you distribute this x to this term, this x and that will reduce out. So lucky for us, we're left with just 1 minus 3x. And then here, when you distribute x to 3, we get 3x. And this is starting to look good. Now I got x over 1 minus 3x plus 3x. Well, that's just 1, and it equals x. Yahoo! So that's proving that they're inverses, because think about it, like the inverse is like undoing everything to the function. So you should just be left with what you put inside this function. And so what I would like you to do is try to do the other way. It should equal x as well, because order matters with compositions. So you try that on your own. And if you don't get x, then you know you did something wrong and you can reach out to me.